So what I mean by linear is that we are not asking for the contents, the disk, like everything in here. That's not part of the allowable set of solutions, or what's sometimes called the set of feasible solutions. We're only allowing on the circle itself, sometimes this is called the disk. So not on the disk, but just on the circle itself. So just on the perimeter of the circle. So I'll call that linear, although that's a little bit misleading. Okay, we're going to review linear and ridge regression, and we're going to see what, if any, relationship there is between ridge regression and the Lagrange multipliers. So actually, I might have a notebook for you, but let's just move on anyway. So first of all, we know what linear regression is. It's from statistics and also machine learning, and the goal is to model the relationship between a dependent variable, the output variable, and the explanatory variable, or the independent variable, or the input variable. Those are all just different words for those terms. Anyway, we have y as a function of x, and x, as we've said before, might just be a single value, but it could be stand for x1, x2, x3, and so on. But we'll say more generally it's a vector. And we talked about the need for ridge regression. One of the needs is for overfitting, and another is for multicollinearity, which is high correlation among the predictors. So ridge regression basically throws in an extra term, what we could call a regularization term. So we talked about the slope squared, and when I say we throw in an extra term, we throw in an extra term in what we're trying to minimize. So we know that we're trying to minimize the sum of the squares of the residuals. So here's our green regression line. That's supposed to be a line, and the dots are blue, and the residuals are the red. So we want to minimize that. But when we do regularization or ridge regression, we add in an extra term, and that is the slope squared. And I said several times that it seems strange that we want to minimize the slope, because there's no reason to do that. I mean, we just want to find the best slope. There's no incentive. It doesn't seem like there's any incentive to minimize the slope. But we talked about when you have multiple variables involved, that we don't want any one variable having too large a coefficient. So the slope is the coefficient for each variable. So it says we penalize large coefficients in the model. This penalty hopes in reducing overfitting and dealing with multicollinearity. Remember that it introduces what we could call bias into the model, because sort of weakens the overall power of the model. It's not going to fit the data as well in any given data set, but it won't overfit the data, and it hopefully will generalize better with new data, and we won't get as much variance in the model as well. So here's just a picture of some data. The input variable feature, we could call it the feature, and the output variable, we could call it the target, and of course we just have a line that fits it. So when we fit that line, we apply ordinary linear regression, and linear regression aims to find the linear relationship between the feature and the target by minimizing the sum of the squares of the residuals, which is the difference between the observed value, which is the blue dots up here, and the green predictions. Remember, we call the blue dot, the height of the blue dot, we label it as y, and the predicted value we would label as that. And since we want to refer to each one of them, we might put like a y1 for the first one, and a y hat 1 for the first prediction, and y2, y2, y3, y3, so we just call them yi in general. So here's the formula that we're trying to fit, we can say, and it's just a straight line here. And then we also say, oh, but there could be, we recognize that there's going to be some error or some residual. So this is not y hat. If we said y hat, we wouldn't need that epsilon, because y hat is exactly the points that, or the y's that lie exactly on the line, not plus some error or some residual. But the actual points don't lie on the line. So this is the line. This is the equation for the line, or the right-hand side of the equation for the line. But then we have to add in we're just adding in the fact that we recognize that the actual y, this is not y hat, will not lie on the line in general. There'll be some residual, or might call it some error. And then y is the target variable. We have this coefficient and this coefficient. This is the input value, and the epsilon. Epsilon, we can call it the error term, or the residual. So they say we fit the model to our data and then use it to make predictions. The resulting line represents the best fit to the data points according to the least squares criteria. So that's our criteria for fitting the line. We didn't have to use squares. We said we could have used something else like the absolute values, but we do use squares, so it's called the least squares criteria for measuring the error. So for that data that we looked at in the graph, this is the model, the red one, and that apparently has a slope beta 1 of that, and has a y-intercept beta 0 of that. Sorry, got that wrong. And then a coefficient beta 1 is this. So the slope is this, and the y-intercept is this for that red line. Now, in that equation, in this equation here, we can say that this represents all of our data. So what do I mean by that? Well, our data is kind of, we can say it's a matrix, and we could say there's the x and the y. So, so we have many rows though. So we can talk about the x as a matrix and the y as a matrix, a column. The y we can say is a column vector, or we can call it a column or a matrix with just one column. And the x can also be like that, a vector or a column. But notice we write the x with a capital X to allow it to be a matrix, and to allow it to have actually more than just one column. We can have like an x1 column, and then also an x2 column, and so on. So then it's going to be more than just a one-column vector or a one-column matrix. It's going to be a multi-column. So we can allow x to have that property. So y is a n by 1, so that's n means n rows, so it's a column vector, and is the number of observations, the number of points in our data set. Beta 0 is a scalar. It's the same, we get the line, so we only have one beta 0, it's the scalar. We only have one beta 1, we only have one y-intercept and one slope. So those are scalars, they're not vectors. And x is same as n in terms of dimension, but it could be have more than one column. So in multiple regression, that means more than one x, like x1, x2, and so on. X would be a matrix of n by p, where p is the number of independent variables, like x1, x2, xn. I'm sorry, xp. They're using p. xp. And then epsilon is also actually a vector, because there's a different error for each y, for each output, right? We have a different red part, so there's a different error. So we need to collect all of those errors. So that's also going to be a vector or a matrix with one column. So representing the error for each observation. And our goal is to estimate the betas. We want to get the betas. We want to know what the red line is. Our goal is to get the red line, means we want to get the betas. Now, they use the word estimate there. They use the word estimate. So why do they say estimate the betas? Because that means that we don't really know. We won't know what they are, in fact, truly. We can only estimate them. And we talked about that. We said these green X's here, these green pieces of data, those are just a subset of all possible data. So we can fit a line to those green dots. We can get the best line, but it's not going to be the best line for all possible data. So we don't know, we'll never know all possible data. We'll never know the real slope and the real y-intercept. So the slope and the y-intercept of the red are just estimates for the slope and the y-intercept of the real one, the true one. So that's why they use this word estimate. Okay, so now we're going to talk about ridge regression, and that's different, or it's a little bit different. So before, we could say that what we were trying to do was minimize the red. So there's so many different lines I could draw between these three dots. I want to choose the line which minimizes the red. If I drew a different green line, like over here, maybe there'd be more red, more error. So what we're trying to do is choose the green line such that the residual sum of the squares, that's the red, or the square of the red, which is written as RSS, residual sum of squares, is as small as possible. So we can say our goal is to minimize the residual sum of squares. Find the green line that does that, or find the beta 0 and beta 1 that does that. Now this part over here is just an expression for the residual sum of squares. So, we have this is not y hat, so this is the actual y, and this part here is y hat. Okay, so this is exactly the residual sum of squares, isn't it? Well, let's see, there's a couple sigmas here. There's this one here, and there's this one here, so let's figure this out. So let's start from the inside out. So here's the inside sigma. So actually, if you notice this sigma and you notice this p, that will help us figure out what's going on here. So the p, remember the p, we said that xx could be, well, first we said it was just a single column, but we said it could be could have p columns. And that meant that we had more than one independent variable. So we might have x1 and also x2 and so on. We can have up to xp input or independent variables. So that's this p here. Here. That's the p. So what are we doing? We're summing up from 1 to p. What does that mean? We're summing up over the variables, the independent variables. Now, what's this? What's this thing here? This is j, right? So that means that's this thing here. So that means that we're summing up over all of the independent variables when we change this j. But don't forget, we also have a sigma outside. This is the inside sigma, but there's also an outside sigma. This is like in programming, this would be like a nested loop. That's what nested sigmas are, really. Or I could say that's what nested loops are. They're nested sigmas. Except sigma specifically means add, but looping is not only for adding. But anyway, let's just say that. So the outer loop, so to speak, or the outer sigma, is iterating over I. So this I will be fixed, like it might be I equals 1. And we will add up all for, so this means for the first row of, we have a data set. So we have a lot of x's, x1, x2, xp. We only have one I. But for the first row, what do we want to do? We want to calculate our prediction based on the x. And we want to subtract that prediction from the actual. So here's the actual, right? This doesn't have a hat on it. And this stuff in here, in the green, is the predicted. So we take y minus the predicted. But how do we get the predicted? We have to, we have an equation like this. We get an equation that gives us our prediction y hat. What is that? It's the line, the equation of the line. And that has a beta 0 plus beta 1. For each row, we have a x. This is a x. This is in the first row, so it's x1, 1. Can't write that very well. x1, 2. That's supposed to be a 2. x1, 3, x1p here. So we have all these different x's, and we multiply them by their coefficients and add them all up. That's what we're doing here. And then we also add in the what do you call it? the constant term or the y-intercept term, and that's our y hat. So that's what we are doing right here in the green. So we're just doing that for the first row and subtracting the actual value minus the predicted value, and then we're and then that's going to give us the first error, the first red, and then we're going to do it for the second row. That's the second point. That's going to give us our second red. I'm talking about these reds. So we're going to get for the first row, we're taking y minus its predicted. That'll give us the first red. Then the second red would be the second I equals 2 here, and so on, all the way up to the end, to the nth row. And here I only have 3 dots, so there'd only be 3 rows. But we would just sum all of that up to sum up all of these reds, and then we want to square all of that. Hopefully, yeah, actually we want to square it first and then sum it up, sorry. We want to square it first. We're going to square this distance and square this distance and square this distance, and then sum them all up. And that's, and we want that to be as small as possible. And when we say we want it to be as small as possible, what can we change here to make it bigger or smaller? What we can change is use the green line, or use a different green line, or use a different green line, and so on. And one way to identify a green line is by saying what its slope and what its y-intercept are. So we are minimizing over the different choices of the different slopes and y-intercepts, and we call actually beta, we didn't really say this before, but this beta is actually like a vector in the sense that it's not just one, it's not just beta, it's not just the slope, it includes the slope, so that's called beta 1. We could have more than one slope, we could have more than one coefficient, because we might have many input variables. Let's say we just have one input variable, then we'd have one beta, we just have beta 1, but we'd also have beta 0, and so together we could call that like a vector, and that's really what this is supposed to be, a vector right there. So that's what all of this means. So we're just saying we want to minimize the squares of all this stuff. So you should make sure that you're clear about all of this, what this is, so j, and that j goes here, and then what this is, the I, and this I goes here, and the I is talking about the number of rows, and the j is talking about the number of input variables, or like the number of columns except for the y, and so on, that we want to minimize over the beta vector, we can say, because there's more than one beta, so we can put it together and call it a vector, put them together and call them a vector, and we could even have more betas if we had more input variables, so it would be like a longer vector. But we want to minimize over that. Those are the choices. That's the way we can change this calculation. We can get a different calculation by having a different line, sort of by having different betas. So all of that is just standard regression. It's just a way of writing the standard regression problem. This is not the standard regression. This is throwing in the ridge regression issue and saying, once we throw it in, the minimization actually, I said the minimization just occurs from here, but if you look at these brackets here, they actually go from here to here, don't they? So we're actually minimizing not just over this, but also over this. So we've changed the problem. The standard one is just over here, but now we're talking about ridge regression. We've changed it, and we put in this extra term. So what does this extra term do?